A Cartesian coordinate system is a coordinate system that specifies each point uniquely in a plane by a pair of numerical coordinates, which are the signed distances to the point from two fixed perpendicular directed lines, measured in the same unit of length. Each reference line is called a coordinate axis or just axis of the system, and the point where they meet is its origin, usually at ordered pair. The coordinates can also be defined as the positions of the perpendicular projections of the point onto the two axes, expressed as signed distances from the origin. One can use the same principle to specify the position of any point in three-dimensional space by three Cartesian coordinates, its signed distances to three mutually perpendicular planes. In general, n Cartesian coordinates specify the point in an n-dimensional Euclidean space for any dimension n. These coordinates are equal, up to sign, to distances from the point to n mutually perpendicular hyperplanes. The invention of Cartesian coordinates in the 17th century by René Descartes revolutionized mathematics by providing the first systematic link between Euclidean geometry and algebra. Using the Cartesian coordinate system, geometric shapes can be described by Cartesian equations, algebraic equations involving the coordinates of the points lying on the shape. For example, a circle of radius 2, centered at the origin of the plane, may be described as the set of all points whose coordinates x and y satisfy the equation x2 plus y2 equals 4. Cartesian coordinates are the foundation of analytic geometry, and provide enlightening geometric interpretations for many other branches of mathematics, such as linear algebra, complex analysis, differential geometry, multivariate calculus, group theory and more. A familiar example is the concept of the graph of a function. Cartesian coordinates are also essential tools for most applied disciplines that deal with geometry, including astronomy, physics, engineering and many more. They are the most common coordinate system used in computer graphics, computer-aided geometric design and other geometry-related data processing. History. The adjective Cartesian refers to the French mathematician and philosopher René Descartes. The idea of this system was developed in 1637 in writings by Descartes and independently by Pierre de Fermat. Although Fermat also worked in three dimensions and did not publish the discovery, both authors used a single axis in their treatments and have a variable length measured in reference to this axis. The concept of using a pair of axes was introduced later, after Descartes' La Géométrie was translated into Latin in 1649 by Franz van Schooten and his students. These commentators introduced several concepts while trying to clarify the ideas contained in Descartes' work. The development of the Cartesian coordinate system would play a fundamental role in the development of the calculus by Isaac Newton and Gottfried Wilhelm Leibniz. Nicole Osmer, a French cleric and friend of the Dauphin of the 14th century, used constructions similar to Cartesian coordinates well before the time of Descartes and Fermat. Many other coordinate systems have been developed since Descartes, such as the polar coordinates for the plane, and the spherical and cylindrical coordinates for three-dimensional space. Description: one dimension. Choosing a Cartesian coordinate system for a one-dimensional space, that is, for a straight line, involves choosing a point O of the line, a unit of length, and an orientation for the line. An orientation chooses which of the two half-lines determined by O is the positive, and which is negative. We then say that the line is oriented from the negative half towards the positive half. Then each point P of the line can be specified by its distance from O, taken with a plus or minus sign depending on which half-line contains P. A line with a chosen Cartesian system is called a number line. Every real number has a unique location on the line. Conversely, every point on the line can be interpreted as a number in an ordered continuum such as the real numbers. 2 dimensions. The Cartesian coordinate system in 2 dimensions is defined by an ordered pair of perpendicular lines. a single unit of length for both axes, and an orientation for each axis. The lines are commonly referred to as the x and y-axis, where the x-axis is taken to be horizontal and the y-axis is taken to be vertical. The point where the axes meet is taken as the origin for both, thus turning each axis into a number line. For a given point P, a line is drawn through P perpendicular to the x-axis to meet it at x, and second line is drawn through P perpendicular to the y-axis to meet it at y. The coordinates of P are then x and y, interpreted as numbers x and y on the corresponding number lines. The coordinates are written as an ordered pair. The point where the axes meet is the common origin of the two number lines and is simply called the origin. It is often labeled O, and if so, then the axes are called ox and y. A plane with x and y axes defined is often referred to as the Cartesian plane or xy plane. The value of x is called the x-coordinate or abscissa, and the value of y is called the y-coordinate or ordinate. The choices of letters come from the original convention, which is to use the latter part of the alphabet to indicate unknown values. The first part of the alphabet was used to designate known values. In the Cartesian plane, reference is sometimes made to a unit circle or a unit hyperbola. 3 dimensions. Choosing a Cartesian coordinate system for a 3-dimensional space means choosing an ordered triplet of lines that are pairwise, perpendicular, have a single unit of length for all 3 axes, and have an orientation for each axis. As in the 2-dimensional case, each axis becomes a number line. The coordinates of a point P are obtained by drawing a line through P perpendicular to each coordinate axis, and reading the points where these lines meet the axes as 3 numbers of these number lines. Alternatively, the coordinates of a point P can also be taken as the distances from P to the 3 planes defined by the 3 axes. If the axes are named x, y, and z, then the x-coordinate is the distance from the plane defined by the y and z axes. The distance is to be taken with the plus or minus sign, depending on which of the 2 half spaces separated by that plane contains P. The y and z coordinates can be obtained in the same way from the xz and xy planes respectively. Higher dimensions. A Euclidean plane with a chosen Cartesian system is called a Cartesian plane. Since Cartesian coordinates are unique and non-ambiguous, the points of a Cartesian plane can be identified with pairs of real numbers, that is, with the Cartesian product, whereas the set of all reals. In the same way, the points any Euclidean space of dimension n be identified with the tuples of n real numbers, that is, with the Cartesian product. Generalizations. The concept of Cartesian coordinates generalizes to allow axes that are not perpendicular to each other, and/or different units along each axis. In that case, each coordinate is obtained by projecting the point onto one axis along a direction that is parallel to the other axis. In such an oblique coordinate system, the computations of distances and angles must be modified from that in standard Cartesian systems, and many standard formulas do not hold. Notations and conventions. The Cartesian coordinates of a point are usually written in parentheses and separated by commas, as in OR. The origin is often labeled with the capital letter O. In analytic geometry, unknown or generic coordinates are often denoted by the letters in the plane, and in 3-dimensional space. This custom comes from a convention of algebra, which uses letters near the end of the alphabet for unknown values, and letters near the beginning for given quantities. These conventional names are often used in other domains, such as physics and engineering, although the letters may be used. For example, in a graph showing how a pressure varies with time, the graph coordinates may be denoted t and p. Each axis is usually named after the coordinate which is measured along it, so one says the x-axis, the y-axis, the t-axis, etc. Another common convention for coordinate naming is to use subscripts, as for the n coordinates in an n-dimensional space, especially when n is greater than 3 or unspecified. Some authors prefer the numbering These notations are especially advantageous in computer programming. By storing the coordinates of a point as an array, instead of a record, the subscript can serve to index the coordinates. In mathematical illustrations of two-dimensional Cartesian systems, the first coordinate is measured along a horizontal axis, oriented from left to right. The second coordinate is then measured along a vertical axis, usually oriented from bottom to top. However, computer graphics and image processing often use a coordinate system with the y-axis oriented downwards on the computer display. This convention developed in the 1960s from the way that images were originally stored in display buffers. For three-dimensional systems, a convention is to portray the xy plane horizontally, with the z-axis added to represent height. Furthermore, there is a convention to orient the x-axis toward the viewer, biased either to the right or left. If a diagram shows the x and y-axis horizontally and vertically, respectively, then the z-axis should be shown pointing out of the page towards the viewer or camera. In such a 2D diagram of a 3D coordinate system, the z-axis would appear as a line or ray pointing down and to the left or down and to the right, depending on the presumed viewer or camera perspective. In any diagram or display, the orientation of the three axes, as a whole, is arbitrary. However, the orientation of the axes relative to each other should always comply with the right-hand rule, unless specifically stated otherwise. All laws of physics and math assume this right-handedness, which ensures consistency. For 3D diagrams, the names abscissa and ordinate are rarely used for x and y, respectively. When they are, the z-coordinate is sometimes called the applicate. The words abscissa, ordinate and applicate are sometimes used to refer to coordinate axes rather than the coordinate values. Quadrants and octants. The axes of a two-dimensional Cartesian system divide the plane into four infinite regions, called quadrants, each bounded by two half-axes. These are often numbered from first to fourth and denoted by Roman numerals I, 2, 3, and V. When the axes are drawn according to the mathematical custom, the numbering goes counterclockwise starting from the upper right quadrant. Similarly, a three-dimensional Cartesian system defines a division of space into 8 regions or octants, according to the signs of the coordinates of the points. The convention used for naming a specific octant is to list its signs, e.g., or. The generalization of the quadrant and octant to an arbitrary number of dimensions is the orthant, and a similar naming system applies. Cartesian formulae for the plane distance between 2 points. The Euclidean distance between 2 points of the plane with Cartesian coordinates this is the Cartesian version of Pythagoras's theorem. In three-dimensional space, the distance between points is which can be obtained by two consecutive applications of Pythagoras' theorem. Euclidean transformations. The Euclidean transformations or Euclidean motions are the mappings of points of the Euclidean plane to themselves which preserve distances between points. There are 4 types of these mappings: translations, rotations, reflections and glide reflections. Translation: translating a set of points of the plane, preserving the distances and directions between them, is equivalent to adding a fixed pair of numbers to the Cartesian coordinates of every point in the set. That is, if the original coordinates of a point are, after the translation they will be rotation. To rotate a figure counterclockwise around the origin by some angle is equivalent to replacing every point with coordinates by the point with coordinates. Where thus, reflection if are the Cartesian coordinates of a point, then are the coordinates of its reflection across the second coordinate axis, as if that line were a mirror. Likewise, are the coordinates of its reflection across the first coordinate axis. In more generality, reflection across a line through the origin, making an angle with the x-axis, is equivalent to replacing every point with coordinates by the point with coordinates, where thus, Glide reflection. A glide reflection is the composition of a reflection across a line followed by a translation in the direction of that line. It can be seen that the order of these operations does not matter. General matrix form of the transformations. These Euclidean transformations of the plane can all be described in a uniform way by using matrices. The result of applying a Euclidean transformation to a point is given by the formula where A is a 2 times 2 orthogonal matrix and B equals as an arbitrary ordered pair of numbers, that is, where, note the use of row vectors for point coordinates and that the matrix is written on the right, to be orthogonal. The matrix A must have orthogonal rows with same Euclidean length of 1, that is, and this is equivalent to saying that A times its transpose must be the identity matrix. If these conditions do not hold, the formula describes a more general affine transformation of the plane provided that the determinant of A is not 0. The formula defines a translation if and only if A is the identity matrix. The transformation is a rotation around some point if and only if A is a rotation matrix, meaning that A reflection or glide reflection is obtained when, assuming that translation is not used. Transformations can be combined by simply multiplying the associated transformation matrices. Affine transformation. Another way to represent coordinate transformations in Cartesian coordinates is through affine transformations. In affine transformations, an extra dimension is added and all points are given a value of 1 for this extra dimension. The advantage of doing this is that point translations can be specified in the final column of matrix A. In this way, all of the Euclidean transformations became transactable as matrix point multiplications. The affine transformation is given by, note the matrix A from above was transposed. The matrices on the left and column vectors for point coordinates are used. Using affine transformations, multiple different Euclidean transformations including translation can be combined by simply multiplying the corresponding matrices. Scaling. An example of an affine transformation which is not a Euclidean motion is given by scaling. To make a figure larger or smaller is equivalent to multiplying the Cartesian coordinates of every point by the same positive number m. If for the coordinates of a point on the original figure, the corresponding point on the scaled figure has coordinates if m is greater than 1, the figure becomes larger. If m is between 0 and 1, it becomes smaller. Shearing. A shearing transformation will push the top of a square sideways to form a parallelogram. Horizontal shearing is defined by. Shearing can also be applied vertically.